SwayamPrabha. Digital India. Educated India.
Yeah, yesterday we have been discussing about this particular equation, where it is type D reactions where there is no ash or solid product on the particle. So, then we have derived this equation, and this is the total time required for not total time, this is the time required for a certain conversion, right. So, if I know if it is the two steps controlling, that is mass transfer through the film and also reaction on the surface, if both are controlling, then this is the equation. So, as usual we can also now simplify this for individual cases. If it is film control, we know that K s goes to infinity, that means rate of reaction is very, very large. So, then this term will not be there, because this is 1 by k, this K s is very large. So, this term will vanish. Then we have T film equal to rho b b kg naught Cag n plus 1 by 3 n plus 1. This is the equation 15. Then if I have reaction control, then we know that Kg is very large value. Then the equation is T equal to R rho b b Kg naught Cag into, only this term will be there. So, this will be 1 minus x b to the power of 1 by 3 by, oh sorry, this will be simply K s, yeah, this will be simply K s, yeah. So, this is equation number 16. Oh, sorry. Okay. So, if you look at particularly equation number 16, I do not know, I think in your notes can you check what is the reaction control equation which we got for the other model, where product also is present on the surface. Yeah, it is exactly same, no? It is same. Do you know why it is same? Yeah. So, the other steps do not even if they are there, you do not feel at all. So, it is only the reaction control. Yeah. So, the other two mass transfer steps are faster. So, then this is equivalent to your reaction control, where the other mass transfer steps are not, you are not seeing the mass transfer steps at all, it is only the reaction control. Okay. Whereas, here it is not exactly the same, and you can, depending on this Kg value, again this Kg changes with diameter, right. This is what yesterday we have seen, Kg changes with diameter, and you know that for large particles it is inversely proportional, right, and for large particles, no, for small particles it is inversely proportional, and for large particles it is 1 by square root of, yeah, dP, these two cases, right. So, if you substitute that in this and then try to simplify, then you will get this T is proportional to r to the power, this depends on small particles and large particles, to 1.5 it changes, the exponent changes to 1.5 to 2. Okay. Of course, we can also calculate now what is tau. Tau is conversion for, yeah, 100% conversion, time required for 100% conversion. Then we can calculate tau, and we can also write this is called as T by tau, right. For example, if I write this one as T by tau, yeah, what do you get? Only this will disappear, yeah, but n plus 1 will be there, correct, no? This will not go to 0, right, x b equal to 1, yeah. and here
T by tau equal to 1 minus of 1 minus x power n plus 1 by 3.
yeah, it will be there. Simply x b equal to 0 is x b equal to 1. It will be there. Now this n plus 1 depends whether you have small particle or large particle. For small particle it is half 1. For large particle it is half. That will come there. That coefficient will come there, but that will be there. Okay. And this tau, if I take here, this is straightforward. Only this much will be there. Okay. So then in terms of t by tau also one can write these equations. Good. So you please just think about these things, and with this the two models which I wanted to do we have completed, and they are not very difficult models, they are simple models, and we wanted to make the entire process as a simple process without much complications. And it is said that shrinking core model in most of the time it is valid for gas solid reaction, non catalytic reactions. But what can be the deviations in this model? When can you say that this may not be acceptable? Because no model is acceptable in all the situations, right? Yeah, 100%. That is why we have some assumptions and all that. Yeah, which assumption may not be valid? The first assumption what we made was that isothermal, I think it is a valid assumption, because the particle conductivity is very very large. So generally when the particle, unless otherwise you have highly exothermic reaction. If you have exothermic reaction, that is not valid, because reaction is going on, temperature changes. Yeah, but one thing which is not mainly valid is the sharpness of the shrinking core model. We have nicely drawn one particle and this at center after some time t, we are just saying that that is the shrinking core. That actually will be diffusive. That actually will be diffusive. So that means exactly your CAC is not there, and RC you can never identify exactly that is the sharp boundary. That is one of the things. But anyway, I think people have done experiments and then finally found that this is one of the very well represented model for gas solid non catalytic reactions. Okay, good. Afterwards, a few more things about this one, some more information about this. If I have the shrinking core model, and as I have been telling you that we do not know which one may be rate controlling, there are various ways tau can be used. For example, if you want to plot the whole rate versus temperature, all these things again analytically some information must be in our mind. So I am simply trying to plot my rate of reaction versus maybe with respect to A, okay, or with respect to B, right. So because the other one is nothing but minus dNA by dt, right, equal to minus 1 by B dN by dt. So that is only the relationship. Okay. So if I am able to plot either one of them, how does that look like? Rate of reaction during reaction. During the entire reaction, you do not know which one is rate controlling. Okay. So if you have only one rate controlling, at least we can easily visualize, but here what is that, what we can normally expect is something like this. So this is rate of reaction, and here let me plot with temperature, that will give us an idea which one, which may be rate controlling, right. So I mean logically you can also get the answer for this. At low temperatures generally which will be rate controlling? Reaction rate. At very high temperatures, mass transfer. So at low temperatures the rate may slowly increase like this, okay, and after some time it may go like this. This is one logical way of representing the rate of reaction with increasing temperature. So I can say here that I have this one is reaction control, okay. Yeah, here what is controlling? Yeah, which mass transfer? I have two. Yeah, ash is controlling. So this may be ash controlling, and in between somewhere you may have film control. Okay? And we know at very high temperatures, even the mass transfer through the film may be higher when compared to diffusion through the pores, ash through pores. So, that is the reason why this is the kind of curve we may expect, and as a check, if you do not have which one is controlling, right. So, let me say that you do not know and you did like this, and you got only this portion. That means, you got all the time a straight line till the temperature you have conducted. So, then what is the idea you get? Rate of reaction, and it is only going like this, but it is not going taking this turn and then becoming almost horizontal. No, it is not happening, it is only just almost a straight line. Okay. So, then we can conclude that this may be reaction control, and then here you do not get all this portion when you start at a high temperature, because the temperature range anyway it is not theoretically 0. Okay. So, at high temperatures and you do not know which one is controlling, you are somewhere here. Okay. So, at that time when you are getting almost, there is not much change, even though you are increasing the temperature, it must be mass transfer control, and generally in this shrinking core model it is diffusion control, because diffusion through the pores is generally difficult when compared to diffusion through the film, because in the film, what do you have in the film? What do you have, Shekhar? It is only gas diffusion. So, it is not that difficult, right. So, whereas in the pores, depending on the pore size, if you have very large pores, again that is a different matter. That is what next we would like to try to do. Okay. For truly homogeneous model, what kind of equations we have to derive, but let me finish this whole thing about shrinking core model, then we will go for that homogeneous model. Okay. So, this is one, and based on this, this first paper on combustion, where systematic studies were done on coal combustion, was done by some Yagi and Kuni in the Japan, and they have very beautifully systematically done, even in most of you are not even born at the time, 1955. Okay. So, how beautifully they have done the, okay, I think I have to plot here, experimental so systematically. Coal combustion, Yagi and Kuni, 1955. Okay. So, he plotted, or they plotted rate constants I think because it is actual data, they have input centimeters per second, and here it is temperature Kelvin, and how many rate constants will be there for coal combustion? Here how many rate constants will be there? Rate constants in the sense may be all process, including mass transfer as well as here only 2, but whereas in normal shrinking core model it will be 3, diffusion also comes there. Okay. And here we will have only 2, but you see how beautifully the data has been collected. This is 1000 Kelvin. Okay. 1400, 1800, 2200 Kelvin. This side the rate changes as 10, 100, 1000. Okay, this is 10, 100, this is 1. Okay, 1, 10, 100, 1000. It is a log scale. Sorry. It is semi-log. This is normal and this is semi-log graph. And then I just draw the lines. Okay. So, then yeah, at 100 at 1000 slightly away from that, it starts and this goes to almost like this, that is one line. And then you have for if the diameter of the particle is 1 centimeter. So, then you will have approximately, I want to draw this. Okay. Maximum is somewhere here. Okay. So, goes like this. Yeah. All this is for dp equal to 1 centimeter, and this one is u equal to velocity, right. Yesterday also we have seen the term velocity there when you are deriving 1 centimeter per second. This one is 10 centimeters. This is 100 centimeters. Oh, no, 1000. Yeah. So, this is 1 meter per second, and this is 10 meters per second. Yeah. So, then it is reduced to 1 mm, 1 centimeter to 1 mm. So, that will be again approximately, I would like to draw this. Okay. This is for dp equal to 1 mm. Again here we have 1 centimeter u, 1 centimeter per second, 10 centimeters, 100 centimeters, no, not 1 meter. This is 1 meter and this is 10 meters per second. So, finally, you also have for dp equal to 0.1 mm. Yeah. Point one mm. Here the velocities are 1 and 10, both are same here. 1 u equal to, this is 1 also 10 centimeters per second, and the next one is 1 meter per second. This is 1 meter, and this is 10 meters per second. Yeah. All that I have patiently drawn just to ask you how to interpret the data. Okay. In the examination, I am very dangerous man. In the examination, I will give that graph and then ask you, okay, write about that. What do you predict? But that is very good training, I say, because that is what you do in your PhD or in your whatever you do research. Okay. You draw the graph, collect the data, and then try to interpret what is happening. Okay. So, this regime is which controlling? Low temperatures. This is reaction control. And here, if I draw this line something like this, something like this, something like this, something like this, all these lines. Yeah. So, this line, okay, this line will give me the k value, ks value, this one, okay, and this line will give me kg value. Right, from here to here. Now, of course, these values are actually given by them. These are all k values. Okay, these are all kg values. But you see, it is increasing like this, and here the asymptote where truly I have the mass transfer control. So, the simple reaction rate for this is minus R A equal to C A G by 1 by K G plus 1 by K S, that is the one. Okay. So, low temperatures, this is infinity, this is controlling, high temperatures, this is Kg is controlling. Okay. So, there are many things, it is not simply I have drawn and then we will just close here. There are many things what you can predict. So, what is happening with increase in dP or decrease in dP? The rates are increasing. Yeah, why? These are the questions. Generally take dP equal to 1 centimeter, 1 mm and 0.1 mm. So, the rate of reaction we say that it is increasing. Yeah, rate of reaction is increasing, Kg increasing. Why Kg should increase? As dP is, yeah, very good. Yeah, that is the kind of interpretation. Okay, we know that as dP is increasing or the Kg is inversely proportional to Kg, the diameter. So, smaller the one, more mass transfer, so more rate of reaction. Okay. So, within the velocities now, you take one particle and now you see 1 centimeter, 10 centimeters, 1 meter, 100 10 meters. So, now again it is increasing. Is it logical? Yeah. So, this is how one has to really present the experimental data, so beautiful. That is why even though it is one of the oldest ones, still it is very highly respected data. Okay. And I mean presently we do not have that kind of patience to collect the data. We will take one point and write 100 models for that. Earlier it was reverse, you take 100 points and then write one model, because modeling is easy now, because you have computers, you have everything. So, okay, and you have packages. So, one data point and then 100 models, but olden style is that 100 data points and one model, which is staying all through, because that is solid model. Okay. So, this is how one has to find out really which one is rate controlling and how do you get the data, all that information you can get from these graphs. Okay. And still the way I am explaining, it is not that simple. Okay. You have now asked me how they have collected the rate of reaction data. Okay. For rate of reaction first, and then only all these things are analyzed, or even here, all that one has to really think before starting the experiment. How do you analyze my data? Okay, I conduct the experiment, but how do you analyze? For example, coal combustion data, how do you find out? You see, we do not have thinking at all, absolutely, particularly with experiments. Imagine that we have one particle and then I ask you to find out rate of reaction. How do you do that?
You can find the change of mass of the coal with time.
How do you find out? Correct, I mean that is right. You can find the weight loss. How do you find out? So, all these things you have to imagine. No, I mean no one is going to tell you if you get the job. Shaker? So, that is one thing I thought I will ask you. You asked me before that. You just told on your own, not asked. First of all, you have two phases there. Okay, gas and solid. Which one you are concentrating? What Anurag was telling was that okay, solid also can be followed. Gas also can be followed. Right? If it is gas, oxygen concentration has to be monitored in the outlet. But normally in the combustion process, you send lot of oxygen and you do not worry. So, you may not have. Yeah, that is another indirect way of finding out. Okay, then you can convert into how much oxygen has been. Okay, so then what are the methods you use for analyzing gas? I am just trying to think. I will make you think. Yeah, if you do not have GC, because people I think 100 years back or 70 years back, I do not know, they do not have GCs. How they could have done it? Gas? You have totally forgotten about this one, no? Titrations. Totally forgotten. No one is doing titrations nowadays, I think. Yeah, that is like Bullock cart technology. That is solid all the time. If nothing is working, Bullock cart will work, because nothing happens to Bullock cart normally, because there is no high funda mechanism there, nothing to get spoiled there. Okay. So, that is why this titration thing analysis is always valid, but because we do not have patience, that is why we are running after fast analysis. Yeah, GC is one. I think it is fair to accept that GC is one. Anything else? Otherwise, actually you have to do, you have to collect the samples, take the samples and then dissolve in something else. If you are following CO2, take the sample or allow the outlet gas itself go through some other chemical where all CO2 is absorbed, and then indirectly you will find out how much CO2 is absorbed. Then you calculate what is O2 would have reacted, all that. Okay. And okay, as Anurag said, I think if you want to find out the weight, what is the technique you use? You heard of TGA? Abhinav, you heard of TGA? No, you said TGA or something. You did not say anything. Huh? Weighing scale. Of course, the principle of TGA is weighing scale only. Yeah, originally people have done that. They constructed a very sensitive balance, and one side they used to put coal particle, maybe 10 grams or 20 grams or 50 grams, and then the other side it is balancing the weight. And you have, I think in your I do not know whether you have done the drying experiments. That is one of the principles. We also constructed that long time back. Okay. So, then you can find out what is the weight change, and that weight can be converted into moles, and of course, moles per unit time, and then you can find out what is the rate. Okay. So, all these things we do not normally tell, all these things we do not normally tell. It is exactly like our movies, where I think I have been telling this, I think last class also I would have told this. All our movies, how does the movie start? With a young boy and young girl coming, and then first either fighting or I mean first sight they never fall in love. Even though they fall in love, I think egoism, they do not accept. So, that is why a boy has to pay in the girl, girl has to pay in the boy, and then till interval it will go over. After interval, I mean in between we have some songs and all that, I think over all that. So, after that only villain comes. Villain may be in the form of mother, mother-in-law for both sides, or father, father-in-law. So, like that brother, brother-in-law, sister, sister-in-law. So, we have in India so many relationships. So, you can, that is the variation in all our movies. One movie will have brother, another movie will have sister, another will have Chittappa also. Okay, so all kinds of people we will have. So, then anyway after that I think everyone will accept, and then the movie ends with marriage. That is all what we show. All the problems actually start after marriage. How many of us I think really seeing those movies? These also exactly like that. We think that we are not telling you all that. Simply I plot rate versus concentration, rate versus temperature, right? But if you do not think properly in your life, you never understand what is that rate, how do I get this rate. That is why I told you, even after PhD can you design a pump, because we would have never told you how to design a pump. You could have solved problems, absolutely no problem, right? You should have solved problems, you could have got yes out of that, in that subject. But finally, when someone asks that, okay, I think I have a problem, I do not know how to calculate my HP for my pump, means I do not know how to calculate. That is why I made a point that every time I will repeat these examples, okay, so that at least you will be aware. You may forget, the moment you cross the door you may forget, okay, like that Matrix movie where he tells that, okay, you do not remember anything the moment you cross the door. So, I am not cursing like that, but I think at least most of you do that, you will forget, and you remember only just before, one day before the examination, and then next day you will again everything will go good. Anyway, so that is why there are so many things when you are teaching a course which is not directly told, like our movies only I am telling, right. There are so many things which you have to really remember, which you have to understand, and for every course general thumb rule of Professor Anant is, if I am teaching 1 hour, you have to work 4 hours at least in your room for that course. That is why we have 24 hours per day and maximum 6 subjects. So, 24 hours, that is the idea, okay, per semester. So, otherwise you do not get anything. You may come and sit and look at me very skeptically, this fellow talks something, I think I just listen, and then otherwise while coming I will drill hole from this side to this side, so that there is no retention there, straight away it comes out, okay, why wasting time. So, that kind of attitude if you come and then you just stare at me, that is all. Otherwise I think at the end you do not get anything, at the end I do not get anything, that I have satisfaction that okay, I taught them where they have understood something and then retained something. Retaining is very important for teacher. Otherwise I think next year semester also if I teach all these things, you come and sit here as if you never heard of this, okay. Yeah, so that is the kind of teaching what we have, and also your response. Anyway, we will close here. Monday will Monday we will meet, and Monday again I can give, for example, derivation of this, okay.